to find delta X and delta H. And that's the only new data you need. You'll get the times the same way as before on the oscilloscope. Okay. Okay. You know, all the talk about gliders makes me think of flying in a field. So I'm going to give in to my instincts. Give me a moment as I go into the next room. Gliding into a field. La da 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 da. La da 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 da. Oh, gliding into a field. I feel so free. I feel so free. And here we are. So at peace. All right. Now, so I'm focusing in now on the triangle that's formed by delta X and delta H, and then delta big H, which is going to be our measured at first. Now, delta big H is mainly for the change in potential energy. And we're going to find it two ways. The first way we're going to measure it, but we're going to find it based on those values we just had. So let's see here. We're going to use similar triangles, or you can just use the sine of theta, whichever way you prefer. So let's see, sine of theta. Okay, well this equals, in the first triangle, let's see here, opposite delta H measured over hypotenuse D. Ah, well, theta is also here, so that also equals delta lowercase h over hypotenuse delta x. And then this gives us what we need. This gives us our first way to find delta H measured will equal delta lowercase h, which we measured, times D over delta X. There you go. That's how you find delta H measured. And notice you can also find the sine of theta. Alright, so now we need the times again, and we need the velocities again, just like before. So, for example, VC will equal minus the length of the glider divided by T6 minus T5, just an example, but that's all the same as before. Now, what we're going to do with this is we're once again aiming to find the acceleration of friction, but instead of Newton's laws, we'll use the conservation of energy. Yeah, okay. So let's look at this. So this is a zoomed in picture. Remember, this is the top of laser 1, the bottom of laser, the top laser and the bottom laser. And then this is delta H. And we're going to find delta H another way. And so up here is delta H, and then down here we're going to call H0. All right, so now the conservation of energy. What does the conservation of energy say? It said that no energy is created or destroyed. Okay, great. So if I have some sort of reaction going on, like an experiment, and I add up all those energies, well, it should be equal to 0. All right? Otherwise, energy would be created and destroyed, and we can't have that. So let's see here. So let's just concentrate on the down direction at first. Let's just concentrate on the down. Okay, so there's a change in kinetic energy, plus a change in potential energy, and then plus all the other energies that aren't considered in those two. Delta E other. And we're going to call delta E other Q for a change in thermal energy. We're just going to sum it all up as a Q change in thermal energy. All right, so that boils down to this. All right, so we have kinetic energy at B. Okay, so good. So that's 1/2 mv VB squared. Great. We have all this. We have the VB from the times, and we have the M because we measured it. Great. No, go. Great. So then minus 1/2 MVA squared. Okay. So far, so good. And then plus, let's see, the potential energy at B is 0 because that's what we're calling the height 0. Calling the height 0 there, so the potential energy there is 0. Aha. And then minus mg delta H. Mg delta H plus Q equals 0. Okay, and now a little bit of algebra. I'm going to keep Q on one side, take everything, throw it on the other side. Okay, so now Q, let's see, this is 1/2 MVA squared plus mg delta H minus 1/2 MVB squared. Okay, so let's see if we can make a little bit more sense of this. Let's say, look at this. This is the complete energy at the upper photo gate, at point A. Okay, so we're going to call all of this the total energy U at A. And then this, the 1/2 MVB squared, because the potential energy is 0 there, that's the total energy at B. So I can write Q as UA minus UB. Okay, so if I did this whole thing again, and then this time I looked at the upward direction, I could now have 2 expressions here. In other words, the one from before, Q is UA minus UB. And now Q is UC minus UD looking at the upward direction, so I have 2 expressions for Q. If I set Q equals Q, then I have this, UA minus UB equals UC minus UD, and then through algebra, I can derive this. A new way to find delta H. We call it calculated, delta H calculated. 1/4G, and then this. VB squared minus VA squared plus VC squared minus VB squared. And from now this delta H calculated, we can go back and find Q. Great. Okay, now that we have Q, let's take a closer look at Q. Q is the thermal work. Well, that equals the force of friction times D. That D we found earlier on. Well, okay, so the force of friction is Q over D. But the force of friction is also MA. Mass times the acceleration of friction. We're almost there. Then the acceleration of friction is the force of friction divided by M. That's it. So once you find this, another value for the acceleration of friction, you can compare it to the one we found in the previous experiment, and you can also now find the acceleration of gravity with your sine theta and G. And that's it. And to conclude, I'm going back to the fields.